Okay, good morning, everyone. It is my pleasure to introduce the second plenary speaker of today, Jeremie Szeftel from the Sorbonne University in Paris. Jeremie completed his PhD in Paris in 2004 under the supervision of Lawrence Halpern. He was then an assistant professor at Princeton until 2009 and held positions at the École Normale Supérieure, the École Polytechnique, and the Sorbonne University. He was an invited speaker at the ICM in Seoul in 2014 and a winner of the Alexandre Ioannidis Prize of the French Academy of Sciences. He is also a current holder of an ERC Consolidator grant. Jeremie is well known for his prolific work in nonlinear PDE. To mention a few of the many highlights, he has made pioneering contributions in understanding the blow-up dynamics of nonlinear Schrödinger equations in joint works with Merle, Raphael, and Rodniansky, and in understanding the low regularity well-posedness for the Einstein equations, in particular his tour de force proving the L2 curvature conjecture with Kleinerman and Rodniansky. More recently, he has turned to understanding the stability of black hole solutions in general relativity, and that is also what he's going to talk to us about today. So before I leave the stage to Jeremie, let me also award him the medal.
Thank you. Yeah. Okay. Yeah, I have it. For the? Sorry. It's okay? Yeah. Okay, so thank you, Gustav, for the kind introduction. And let me also, And let me also, sorry. And let me also thank the speakers for the opportunity to talk at this conference. It's a pleasure and an honor. Okay, so I'm going to, something's going on. I'm going to present, I didn't do anything. I'm going to present the black hole stability problem. So I'm going to introduce it. We already saw many of the things I'm going to say at the beginning of the talk in yesterday's talk by Peter Hinz. But I find that repetition is not necessarily a bad idea, in particular in GR. And then I'll move to the history of this problem after having presented the conjecture. And then I'll present you some results which are joint work with Sergio Kleinerman. And I hope to have the time to explain some of the ideas behind these results. Okay, so let me start with the evolution problem for Einstein vacuum equations. So we are starting with Lorentzian manifold. So you have a manifold M of dimension 4, 1 for time and 3 for these 3 dimensions for space, and a metric G which is Lorentzian. In other words, it has signature minus, plus, plus, plus. The simplest example is the Minkowski spacetime. So the manifold here is R1 plus 3, and here I'm providing the Minkowski metric in Cartesian coordinates. So it's minus dt squared plus dx1 squared plus dx2 squared plus dx3 squared. So I'm going to look at the Einstein equations in the vacuum, in other words, in the absence of matter. And in that case, they reduce simply to such Lorentzian manifolds with a vanishing Ricci tensor. So the Ricci tensor is a symmetric to tensor, which is the trace of the curvature tensor, the curvature tensor itself being a 4 tensor containing all information on curvature. So here you're asking that your Lorentzian manifold have certain curvature combinations that are 0. Okay, so let me immediately mention an important property for this talk, which is the one of general covariance. So general covariance is the fact that you're not looking at a single solution, you're looking instead at a class of equivalents of solutions modulo diffeomorphism. So another simple way to state this is the fact that these equations, Ricci is equal to 0, are invariant under change of coordinates, so, and which reflects physically the fact that laws of physics should not depend on the particular coordinate system you pick. Okay, so later in the talk it will play an important role, but let me immediately use this fact to write the Einstein equations in a simple form just so that you get a sense of these equations. And here I'm going to use the form used by Peter Hintz in his talk yesterday, even though this is not at all the form I use I'm going to use in the results I'm going to present, but it's just for this slide to keep in mind some properties of the equations. Sorry. So here I'm going to pick a particular coordinate system. Due to general covariance, I can choose a coordinate system. So let me pick a simple coordinate system called wave coordinates, in which case the Einstein equation reduced to this simple, at least maybe more approachable system of PDEs, which is a coupled system of nonlinear wave equations in the coefficient of the metric G alpha beta. So here you have the D'Alembert in the metric G of the metric coefficient is equal on the right-hand side to a nonlinearity depending on the metric and first-order derivatives on the coefficients of the metric. And in fact, if you count, you have 10 equations when you're in dimension 1 plus 3. Okay, so since this is a system of wave equations, this is clearly an evolution problem. And let me recall this celebrated result of Yvonne Choquet-Bruard and later Choquet-Bruard-Brioche, which is the fact that for sufficiently smooth initial data, and let me not say more, the Einstein vacuum equations are well posed, and there exists a unique maximal solution. Okay, so the local existence result is due to Choquet-Bruard, and the notion of maximal solution, which is actually non-trivial in GR due to the general covariance, is due to Choquet-Bruard-Guéroche. Okay, so once you have this result of local existence, the natural next step is to wonder what happens in the large for these maximal solutions. So you'd like to know what happens for large time. What is the asymptotic the Einstein equations for large time? In general, this is obviously a very difficult question, but let me stick to a simpler problem, which is the one of understanding the flow of the Einstein equations, the evolution of the Einstein equations near particular stationary solutions. So here on this slide, there is already one stationary solution. That's the Minkowski spacetime. It's flat and therefore Ricci flat in particular. So this is the first and the simplest, in fact, solution. And let me present two other solutions, which we already saw yesterday in Peter's talk, which are the Kerr and Schwarzschild solutions. Okay, so let me give you the Kerr matrix in so-called Boyer-Lindquist coordinates, TR theta phi. So here you have this formula, and you can see why Peter didn't want to show it yesterday. It's pretty ugly. But fortunately, most of it is relevant for this talk. What is relevant are the only following observations I'm going to make. The first thing is that I can write down a formula, which means it's an explicit solution to the Einstein vacuum equations. And the second important aspect is that there are these parameters A and M, which means it's not a single solution, but rather a two-parameter family of solutions. So here A stands for the angular momentum, and M stands for the mass. And finally, third observation, if you look at these coefficients, even though they are complicated, they are all functions of R and theta, but not T and phi. So they do not depend on coordinates T and phi, which means that you have a time-independent solution, so it is stationary, and it is also axis-symmetric because it does not depend on d phi. Okay, and now let me single out a subfamily of the Kerr family, which has the feature of being algebraically simpler, so at least the formula it looks nicer. And that's the case where you take the angular momentum to be 0, in which case you get the Schwarzschild matrix, which is thus a sub-one-parameter family of the two-parameter family of Kerr matrix. And in that case, you get, again, a solution which has some symmetry. It's even more symmetric. Now it's strictly symmetric, and it takes the following form. OK, so this form is also irrelevant for the talk, except for the next slide. I just want to make two comments on this explicit formula. The first comment is that when r goes to infinity, the coefficients in front both of dt squared and dr squared goes to 1, in which case you recover, in the case where both coefficients are 1, you recover the Minkowski metric written in spherical coordinates. So that means that as r goes to infinity, which is called special infinity, the solution looks more and more like Minkowski, which is what is called asymptotically flat. So it's an asymptotically flat solution of the Einstein vacuum equations, and I claim the same statement applies to Kerr. And the second observation, which was mentioned both in the talk of Peter and I think the one of Juan Maldacena, is the fact that there is something weird going on at r is equal to 2m. This seems to be there seems to be a singularity in your metric, so this is in fact only a coordinate singularity. You can remove it by change of coordinates, but nevertheless, this hypersurface R is equal to 2m is important. And that brings me to the last property I wanted to mention, which is the main one, in fact, that Kerr and Schwarzschild are black holes. So Schwarzschild more specifically correspond to the particular case of non-rotating black holes, while Kerr spacetime in the restriction absolute value of A is less than m correspond to rotating black holes. Okay, let me repeat the picture of Peter yesterday to understand what is this black hole. So if you start, as we have seen, when R is very large, you are asymptotically flat. So your light cone should look like the one of Minkowski. And then the more you move to the left, the more you drift from Minkowski. Your light cones start tilting to the left. And when you arrive at this special hypersurface R equal to 2m, they are actually tangent to it, which means that light cannot escape anymore. And therefore, the region R less than 2m is what is called a black hole. So here, sorry, I went a bit fast. I forgot to mention this. Well, sorry. This is a picture in the TR diagram, which means that, of course, I'm suppressing 2 dimensions. And I'm using here the fact that Schwarzschild is spherically symmetric, so that each point on this picture is, in fact, a 2-sphere. OK? OK. So now let me state the conjecture I'm going to consider in this talk, which is the stability conjecture of the Kerr family. Okay, so let me repeat that we are in the asymptotically flat case. So we look at asymptotically flat solution to the Einstein vacuum equations. And then you have the following conjecture. So first, you can see that it's not quite the stability of Kerr. It's only stability of a certain region, which is called the exterior region. Why is that so? That's because, in fact, only the exterior of the black hole is expected to be stable. The interior, on the contrary, is, in fact, conjectured to be unstable. And I should say that this is also a fascinating story, which has attracted a lot of activity in the field. But due to lack of time, I'll focus on the exterior region. OK, so what is this conjecture of the exterior region of Kerr? It states that if you start close to an initial condition, or at least sufficiently close to initial condition of an exterior Kerr, with the restriction that the absolute value of A is strictly less than m, which is called sub-extremal restriction, then your solution exists for all time. So you have global existence, you stay close to Kerr, and moreover, as time goes to infinity, you converge in general to another Kerr solution. So we have a different final mass and final angular momentum. OK, so let me immediately, in fact, already start the history. I'm going to review the history of this problem starting with the next slide. But let me immediately start with a very particular member of that family. Namely, when you take formally in the formula of Kerr solutions, you take m is equal to A is equal to 0. If you look at the formulas I showed you, you immediately realize that the only thing that's left is, in fact, the Minkowski spacetime. Of course, it's a very particular member of this family. In fact, it's a singular limit. And the reason is that it's not the same. It does not have the same topology. Minkowski, of course, is flat. It does not have a black hole. So it's a very particular member of this family. But nevertheless, it's, of course, interesting to ask about its stability. And this was a monumental achievement by Christou and Kleinman, which started all this analysis in the field, which was the stability of the Minkowski spacetime. OK, so you might wonder, in view of my conjecture, why is it that you can talk about stability of Minkowski without the rest of the family? And the reason, again, is that this, even though this is in fact a singular limit. In other words, if you start close to Minkowski, you're in fact infinitely far, in a suitable topology, in suitable norm, you're infinitely far from any other member, and that's why you will not converge to another member of the family, and you can just talk about convergence to Minkowski. But as you can see from the conjecture, in general, if you start close to Kerr for any other member, in other words, one that has a black hole, then you will converge to, in general, to a different Kerr. OK, so now let me start with a natural model problem when you look at stability, which is the one of linearized stability. In other words, you look at the linearized equation around your solution. OK, so this you linearize the Einstein equations around a Kerr solution. That's the so-called linearized gravity system. And then the goal at the level of this toy model is to prove decay towards, to prove decay of the solution. In other words, the level of the linearized system, you want to prove that your solutions decay to 0. So there was a large literature devoted to this problem in the 60s and the 70s by many prominent physicists from black hole physiks. And I'm going to review some of these results. But let me immediately mention what you have if you are in the particular case of Minkowski. So this linearized system, it's a priori, it's a large, we started with a coupled system of equations. You expect a large entangled system. It turns out that in Minkowski, this system reduces to a single scalar wave equation on the Minkowski spacetime. So at least at the level of the linear analysis, it's simple, even though, of course, the proof of stability of Minkowski at the nonlinear level is very complicated. Now, in the case of Kerr, it turns out that even the linearized system is really non-trivial. It's a large, there is not this decoupling, and therefore you stay with a large, you are left with a large and entangled system, and it's really non-trivial to be able to actually prove decay for its solutions. Okay, so let me start with the insight given by the physics literature on this problem. And the starting point is very natural. When you have a large and entangled linear system, think of matrices, then obviously if you want to invert a linear system, you want to put your matrix in lower triangular form. That would be a very natural way to invert your matrix. Of course, here you have an infinite dimensional system, but nevertheless, you want to follow the same idea. And if you want to put a matrix in lower triangular form, of course, there is always the top component, and the top component should be diagonal. It should decouple from the rest. So that's exactly what the goal is here. You want to identify a quantity which decouples from the rest of the solution, and from which, in principle, you can reconstruct the whole solution, which means starting from that part, you put everything in lower triangular form, and you recover components one after the other. Now, that was a great achievement of Tucholsky, who was able to exhibit such a quantity at the level of curvature. In fact, there's a long history. There were other attempts before, but let me mention this, which is particularly relevant for this talk. And he could prove that there are certain curvature components. In fact, there are two, which I'm going to refer as psi plus and psi minus for the purpose of this talk, that satisfy a wave equation, which decouples from the rest. In other words, on the right-hand side, I do not see any other component. I just see 0. OK? So here, let me mention the terms in red here, which these first-order terms here are in fact, turns out, makes this equation non-conservative. In other words, it does not derive from a Lagrangian. So we'll see later that this creates problems. But at least if you forget about this issue, you could hope that you can control these scalars. And then, of course, the goal is once you have controlled the Tucholsky scalars, you want to rely on this control to derive decay for the rest of the solution by, again, exhibiting a kind of triangular structure. OK. So let me, so before mentioning the state of the art on this linearized reality system, let me also mention some obstructions. In other words, at the level of the linearized system, you will not be able, in fact, to achieve your goal, will not be able to prove decay of the solutions because there is a kernel. Okay, so you cannot completely invert your linear system. There will be some components you don't control. And let's see where this kernel comes from. Okay, so first, the first obvious members of the kernel comes from the fact that you're not looking at a single solution, but you're looking at a two-parameter family of solutions. And in fact, it is smooth. They depend smoothly in the parameter A and M. So you can start differentiating in these parameters. And you see that the variation with respect to the mass and angular momentum of the Kerr metric is, in fact, in the kernel of the linearized operator. Okay, so that's your first enemies, if you want. Of course, at the nonlinear level, nevertheless, the conjecture says you should be stable. So you have to deal with that at the nonlinear level. And what this corresponds to is the fact that precisely this reflects in the fact that you converge to different final mass and final angular momentum. And this is what is known usually as modulation. So you have to modulate on the mass and angular momentum. OK, then there is a more serious kernel, one which is due, in fact, to general covariance. In other words, because I have this class of equivalence modulo diffeomorphism, I can apply them. I can take the pullback of diffeomorphism of the Kerr metric by this diffeomorphism. And at the linearized level, this reflects in the fact that any Lie derivative of a vector field applied to the Kerr metric is in the kernel of the linearized system for any vector field X, and of course there are infinitely many. So this is an infinite dimensional kernel, and hence a priori much more serious. In particular, typically modulation is usually done in finite dimensions. So this is actually a quite interesting problem. Okay, and to what is this kernel related at the nonlinear level? At the nonlinear level, this would be related to the fact that you do not know in advance where, you know that you're going to converge to Kerr, but you don't know where this Kerr solution is centered. So there is a problem of tracking the infinitesimal motion of the center of mass of the Kerr solution. Okay, so let me now talk about the state of the art on this problem. Okay, so let me start. In fact, there's a, in fact, I should say there is a huge literature. So I really apologize. I cannot do justice to many of the results obtained here. So I'll, for lack of time, I'll mention only some of them, and I'll apologize. And let me, in particular, start with something which I cannot review here because there's a long history, but which is very important for this problem. Sorry, I'm getting, okay, I understand. Okay, let me start with something even apparently much simpler than the linearized gravity system, which is just the same model as in Minkowski, which is just the wave equation on a Kerr background. So this is a scalar wave equation on Kerr background versus the large entangled system of linearized gravity system. So this is certainly even a simpler toy model, but I should say this is already highly non-trivial. I think we saw a glimpse of that in Peter's talk. It's a highly non-trivial problem, and there is a very rich literature on this, and I should say this was one of the major success of the field in the last 15 years to fully understand this problem. So, if I had the time, I would have to quote at least a full slide, if not two, just on this problem. Okay, so now let me come back. Having said that, let me come back to the linearized gravity system. And recall that we have these Tucholsky scalars. You want to control them, but they satisfy a non-conservative linear wave equation, which at first might be surprising because the Einstein equation derived from a Lagrangian, but these Tucholsky wave equations do not. And for this reason, Whiting, in his seminal work, could obtain that the linearized gravity system has no exponentially growing modes, which was already quite an achievement, but he could not a priori establish even formally the boundedness of solutions. And in fact, if you want to be relevant for the nonlinear problem, not only should you prove boundedness, but you should even prove decay, as I said before, and if, in fact, quantitative decay. Okay, so what is the way around this? Well, the breakthrough came from remarkable work by Dafemos, Rotsager, and Rodiansky, where they understood that you can use something known as the Chandrasekhar transform to transform the Tucholsky equations in much better equations called of Regge-Wheeler type, which derive from Lagrangian, on the contrary, and therefore are amenable to the techniques done for the wave. Okay, and that allowed them to, in fact, that was the starting point to control the Tucholsky scalars, but in fact they could control the full linearized gravity system. So then let me finally, so I should mention that there are, in fact, many other works of stability on Schwarzschild, and I apologize for not quoting all these works. I would still like to quote the fact that this was extended later to Kerr linear gravity system for Kerr for small angular momentum by two independent teams. On one hand, Anderson, Begdal, Blue, and Ma, and on the other hand, Hefner, Hinz, and Vashi. And we heard about the second result in the talk of Peter yesterday, even though it's actually of a different, it doesn't follow the strategy I explained here, but rather a spectral approach as we saw in his talk. So these were also both important achievements. Okay, so now let me move finally to nonlinear results. What are we doing? Okay. And let me start with the simplest non-trivial member of the Kerr family, which are Schwarzschild solutions. So here, of course, we saw that they are algebraically simpler, and in fact, as we'll see later in the talk, there are really fundamental, nicer features about Schwarzschild compared to Kerr. And therefore, it's a nice idea to start with it. On the other hand, recall that this is particular case is equal to 0. On the other hand, you cannot hope to prove a stability of Schwarzschild in general. You have to restrict the class of perturbation. And why is that so? Because if you start close to Schwarzschild, the conjecture tells you that in principle you end up close to Kerr. So if you want to force convergence back to Schwarzschild, if you want to force your end state to be Schwarzschild, in other words, the angular momentum, the end angular momentum to be 0, you have to restrict the perturbations. And one simple possibility is to choose a specific class of symmetry which is preserved by the flow and does exclude non-zero angular momentum. So let me not explain exactly what is this symmetry. Let me just say that there is such a symmetry, which is called axial polarized. And this allowed us, in a joint work with Cedric Kleinemann, to prove the stability of Schwarzschild within that class. In other words, this is the analog of the conjecture. In the case of Schwarzschild, you start close to a Schwarzschild metric in this symmetry class, and you end up converging to another Schwarzschild metric. And I should mention that this was recently extended to a well-prepared convention 3 set of initial data by remarkable work by Dafemos, Folsager, Rudensky, and Taylor. And here it's important to understand that codimension 3 set of initial data is actually optimal. You cannot do better than that. Okay, so now let me present also what is known about nonlinear stability of Kerr. And so far results, at least at the level of full nonlinear stability, there's only understanding in the case of small angular momentum, or if you want, slow rotating black holes. Okay, sufficiently small, slowly rotating black holes. Okay, so this is again joint work with Cedric Kleinemann. So I should mention that there is already a preprint out on arXiv. There are parts of the proof that are still being written as of now, but we are confident enough to state the result, which is that the stability conjecture holds true for small angular momentum. And let me show some conclusions here. In particular, the constructed spacetimes have a complete future null infinity, satisfying a boundary mass formula and a future horizon. So if you do not, for non-experts, these statements might not be very enlightening, but let me just say that these are the natural statements you would expect if you are able to prove stability. The final mass, as you should expect, coincides with final boundary mass. And there is a suitable, we can define a suitable notion of quasi-local angular momentum on null infinity, and in fact inside the spacetime too, which converges to the final angular momentum of your solution. So now let me draw yet another connection with the talk of Peter yesterday. He talked in particular about the analog of this problem in the case of a positive cosmological constant. And in particular, he mentioned his remarkable result with joint work with Andreas Schwarzschild, where they obtained the stability of Kerr de Sitter family for small angular momentum in the context of positive cosmological constant, which is the analog of this result, which is that we have here for Kerr, which is in the asymptotic flat case. Okay, let me check a bit. Okay, so in the remainder of the talk, I'd like to mention some of the ingredients of the proof of these two results, both in Schwarzschild and Kerr. Most of what I'm going to discuss concerns, in fact, both proofs. I mean, there's a common framework for both proofs. And then I hope to have the time towards the end to mention what are the new ingredients when the angular momentum, at least the new conceptual ingredients when the angular momentum is non-zero. Okay. Okay, so let me start with the Pendulus diagram of the finite spacetime. So usually when I speak in front of a non-specialist, at least non-expert, not necessarily experts in GR, I avoid Pendulus diagrams, but we saw so many Pendulus diagrams in the talk of Juan Maldacena that I felt emboldened to show you some of those. Okay, so maybe if you remember from the talk of Juan Maldacena, this dotted line, first of all, the Pendulus diagram as the TR representation, it's a different representation, but as in the other representation, this is a plane, so you should think that each point is in fact a two-sphere. Second observation, this is a compactified picture. So it's quite different from the TR diagram. It's a compactified picture. In particular, you see infinity. The dotted line here is, in fact, in reality, it is at infinity. So this is not a real part of your space-time. And it's an infinity that you reach when you go along light cones. In fact, outgoing light cones. So outgoing light cones in this picture are 45-degree lines moving towards the right. And and ingoing light cones would be 45-degree lines moving towards the left. And so this null infinity called scry here is what you get when you follow outgoing light cones all the way to infinity. Okay? So then, of course, this other line here, which in fact is also a 45-degree line, which means that it is also null, it's an outgoing null cone, it's the event horizon. So recall that the event horizon is simply r is equal to 2m. You don't see it in TR coordinates, but in fact this is a null hypersurface, so it's also a light cone. And then, okay, I think that was it for the general Penrose diagram representation. Now let me be more specific about the kind of space-time we have. So first of all, an interesting observation is that we go slightly inside the black hole. The space-time here is delimited by these boundaries here. That's the final space-time, the one you obtain after convergence. And you can see that there is a part of my space-time inside the black hole. It seems to be contradictory with the fact that I said that only the exterior region is stable. Okay, it turns out that, in fact, there is a tiny bit of the interior that's also stable. And for us, it's quite convenient to go inside for the following reason. That means that in the context of our proof, we never see the horizon. We never care about it. And the only thing we care is to close our estimates. And it's only completely at the end, once we have obtained convergence, that we come back and can show that, in fact, there is a horizon and a part of the black hole. But it is, if you want, you don't have to care about it in the process of the proof, which is quite convenient. Okay, now another observation is that there are apparently two different regions in my space-time. There is an exterior region, which is denoted here by mx, and an interior region denoted by mint, and they are separated by a time like, sorry, I know. Yeah, I think I have to keep it, yeah. No, sorry. Okay, they are separated, I get it, okay. They are separated by this time-like hypersurface T, which is, in fact, you should think of at constant R hypersurface with the same R coordinates I provided before. So it's a constant R hypersurface, which means in particular that this interior region, even though it's a compactified picture, so it's very misleading, this exterior region goes all the way to infinity. This is a very large region. This interior region is large if you go in the future in time, but as far as the R coordinate is concerned, it's a bounded region. It's a small region. So you should think that the exterior region here is much, much larger. And in particular, you expect to have probably more problems here. Okay, so now why do I talk about these particular regions? I want to mention that they are foliated differently. So here we choose to foliate it by outgoing null cones, this exterior region. And the interior region, on the other hand, is foliated by ingoing null cones, ones that go towards the horizon. Okay, and finally, let me mention that there is also a function R that I keep talking about. This function R will, if you look at their Level set, it gives you cuts on the cone. In other words, Level set of this function R will give you topological two spheres around the cones. So it's really like in the picture of Schwarzschild you would have in mind. You have null cones, and constant R is going to slice my null cones in topological two spheres. These are not actual two spheres, especially in perturbations, but they have the topology of two spheres. Okay, now so this was the space-time that you obtain at convergence, but it's not the actual space-time you work with. In the proof, you work within a continuity argument, and I want to draw your attention to a particular hypersurface in the spacetimes we work with. So this is, again, the same spacetime as before, but it's before convergence, so it's a continuity argument. I have a finite spacetime, and then I'm trying to push it, and prove that I can push it forever until it goes to the final spacetime. Okay, so it's a typical continuity argument, or proof by bootstrap, if you want. Okay. So first of all, let me immediately mention something quickly and then forget about it. There is an extra region here. I have my exterior region, my interior region. There seems to be a new region. So first, I should say that it's absent in Schwarzschild, but in care, you have to have that region, because what I call null cone before are actual null cone and are legitimate null cone in perturbation of Schwarzschild. But in perturbation of care, for reasons I said at the end of the talk, you cannot actually choose null cone. There is a reason for that, which has to do with non-interoperability, and I mentioned it. So the hypersurfaces are not quite null cones. So let me continue to pretend there are null cones. But in care, you have to add, because there are not null cones, in fact, you don't have a causal region, so you have to have a small region here. But I should mention that it's a local existence region, so it does not create any difficulty. So let me completely forget this aspect. OK, on the other hand, one thing I want to show you is this hypersurface sigma star here. You see, mx is infinite a priori. These null cones, they go towards infinity because the coordinate r goes to infinity along them. So if I want a finite spacetime, I need to stop my light cones somewhere. And I'm going to stop my light cones at sigma star, which you could think of, for instance, if I was in Minkowski, I would stop at t is constant for a large t. OK, in Schwarzschild, you cannot do that forever, but let me pretend that this is what we do. OK, so now I'd like to say that even though it's called a last slice, which is the common terminology that comes from the proof of stability of Minkowski, you should, in fact, it is a kind of first slice in the sense that this is the slice that rigidifies my spacetime. Because once I have chosen this sigma star, then that initialize my light cones, outgoing light cones. So I go down like this. And then from my outgoing light cones, I can initialize my ingoing light cones. I go inside here. And I have covered my whole spacetime. Let's forget about the last region. OK, so that means that my whole space, once I have chosen sigma star, my spacetime is what it is. So I better very carefully choose sigma star. Otherwise, it could very well be that I'm constructing something. And even though the actual spacetime converges to care, if I didn't choose sigma star correctly, I will not recognize it. I will converge to something very weird. So that's why the choice of this last slice is very important, and I'll come back to it later. OK, sorry. Yeah, OK. So now let me mention some of the main ingredients of the proof. I mean, some of the steps we have to do to get a sense a little bit of the structure of the proof. OK, so here I'm going to follow the path that was suggested by the linearized theory, at least in the way I presented it. OK, so the first thing you want to do, remember you have a large and integral system. And at the nonlinear level, you also want to define something that would be the analog, nonlinear analog of your Tucholsky scalars. You want to derive the analog of Tucholsky equations, except that in the nonlinear case, they do not decouple. The linearized problem decouples completely. At the nonlinear level, it couples to quadratic terms, to nonlinear terms. And you want to use a Chandra-Chekhar-type transform to, in the context of the nonlinear problem, to reduce it to a Lagrangian, a wave equation which is Lagrangian. OK, so here I should mention that, well, first of all, that part is actually not yet finished. It's a joint work with Sergio Clement and also Elena Giorgi. And here, an important aspect that you do not see in linearized theory is the fact that the nonlinear terms have to satisfy a very special structure, which, if you heard talks in GR, you hear all the time about, which is the so-called null structure, which is a magical structure which is responsible for the fact that you can actually control the nonlinear terms, even though the actual solution decays slowly in the asymptotic flat case. So this is a very important structure. OK, so then, as suggested by the linearized theory, you want to reconstruct the rest of the solution starting from these Tucholsky scalars. So you need to reconstruct curvature, connection, metric components. And for that, again, you want to exhibit a kind of triangular structure, or at least triangular at the level of linear terms. Of course, at the nonlinear terms, it's coupled. But these nonlinear terms you treat in the context of your proof by bootstrap. OK, so you want to derive suitable decay estimates consistent with the linear theory. And let me mention that for decay estimates, there are actually two types of estimates. You have transport equations along the generator of the null cones. That's that are foliating mx and mint. And then remember, you also have two spheres of intersection. So on these two spheres, you want to use elliptic system of Hodge type. If you want kind of an example would be a difficult system on these spheres. OK, so now this seems very nice. But of course, remember, there is an enemy, which is the presence of the kernel. There are two kernels. And they in fact corresponds to the two equations, the two estimates here. So the kernel corresponding to elliptic estimates has to do with the suitable definition of the mass and angular momentum, and are responsible for the fact that in the end you converge to different final mass and angular momentum. So here, provided you make a suitable definition of the mass and angular momentum, you can kill that, or you can deal with that kernel if you want. So that's modulation in the mass and angular momentum parameter. And then there is also a kernel related to the elliptic system of, to the transport equation along the generator of the null cone. And this is the one related to general covariance, the more serious one, the one that has infinite dimension. And this requires to construct specific spheres that track the center of mass of the solution, or rather the center of mass of the Kerr solution you will converge to. Okay? So this is an important aspect of the proof, and I want to discuss this in my next slide. And finally, so far I just discussed decay estimates, but in these proofs, decay estimates are typically for a low number of derivatives. Think of half the number of derivatives. And then if you want to close, because it's a hyperbolic system and you don't want to lose derivative, then for top derivatives, or at least for high derivatives and top derivatives, you need a different kind of scheme that remembers the hyperbolic structure of your problem. So here you use a first induction on derivatives, energy Moravec estimates whenever you have wave equations, and you also want to use the Maxwell-like character of the Bianchi identities. So Bianchi identities are important identities for the curvature tensor, and that's exactly the identities that give you the hyperbolic structure in your problem, and they turn out to have, they are reminiscent of the Maxwell equations, if you want, and that's how you deal with them. Okay, so that's where you remember the hyperbolic structure of your problem. Okay, sorry, Gustav, how much time do I have? Oh, 15, okay, good, thank you. Okay. Okay, so sorry. So again, so I want to finish this talk with mentioning two aspects. The first is was already announced. I want to tell you more about the special spheres that track the center of mass of the solution. And then at the end of the talk, I hope that I have the time to discuss the new aspects when you move to non-zero angular momentum. In other words, so far, what I describe is the exact same scheme of proof, both for the result in Schwarzschild and Kerr, and I want also to mention what are the new aspects when you have non-zero angular momentum. Okay, but first, let me talk about these special spheres that are supposed to track the center of mass. So we give a special name to these spheres because they are very important in the proof. We call them general covariant modulated, because simply they deal with the kernel due to general covariance, and modulated because this is dealing with the kernel at the nonlinear level is what is the so-called modulation. Okay, so what is the goal with these spheres? So remember, you have these outgoing null cones in the exterior region, and of course, these outgoing null cones, can always they are in a given space-time, even of course, in particular in Schwarzschild and Kerr, there are lots of light cones. But obviously, if I want to recognize that I converge to Kerr, I don't want to converge to any random light cone. I want to converge to a nice light cone that I know very well in my representation, which I gave you a representation TR coordinates at the beginning. Maybe I have a different representation, but certainly I want to converge to preferred light cones, so some nice light cone I will recognize. Okay, so these spheres foliating these light cones should converge to the spheres, the preferred spheres of Kerr. What are these preferred spheres? These are simply the spheres of constant T and R in the coordinate system I gave. So they are special, I can recognize them, and that's what I want to converge to. So in the work in Schwarzschild, we had such a procedure to recover the spheres of Schwarzschild, which in this case are round spheres. But this procedure was relying on the symmetry assumptions. So to move to Kerr, we had to remove this symmetry assumption because we work with general perturbations of Kerr. So in joint work with Sergio Kleinemann, we designed a procedure which extends the one of Schwarzschild and which allows us to construct a unique two-parameter family of preferred codimension two surfaces in general perturbations of Kerr. In other words, I am in perturbation of Kerr. Of course, I lose the exact spheres of Kerr, but I want to find an analog of the two-parameter family of Kerr, parameterized by T and R. I want to find, in fact, for us, it's U and R, but that doesn't matter. I want to find the analog of these spheres. I want to recognize a special family of spheres in my perturbed spacetime. So here, it's very important that this procedure gives you a unique two-parameter family of spheres. And in particular, it is important that this uniqueness statement allows you to check that if you start in Kerr a priori close but not quite at the correct sphere, in fact, the procedure recovers the correct two-parameter family of spheres of Kerr. So if you start nearby, the procedure gives you back the spheres of Kerr, which is a good check already for, if you want, validating your construction. So here I want to relate this construction, in fact, to a celebrated work by Huisken and Yao, where they construct, preferred codimension 1 surfaces in 3 Riemannian manifolds. So here, it's of course an analogous problem, but for us it is actually very important to construct directly codimension 2 surfaces in the Lorentzian spacetime, which is actually hard. Sorry. Okay, so then, let me say briefly something about these spheres. So these spheres rely on fixing well-chosen geometric quantities to agree with their Kerr value. Okay, so that's so the definition. I'm not going to show you this quantity is not too relevant here, but the important thing, of course, is that defining them is easy. What is difficult is to actually show that they exist. So constructing them, showing uniqueness, and in fact other statements like rigidity. Okay, and finally, let me mention another aspect connected to angular momentum and what I called, I think in the slide where I presented the result, quasi-local angular momentum. So what is quasi-local angular momentum? It's a notion of angular momentum that doesn't make sense in the whole spacetime, but just, let's say, on a closed surface. And here, of course, I'm thinking of these spheres here, of these special spheres. So it turns out that on these special spheres, I can define an intrinsic definition of angular momentum. And furthermore, that's another aspect I did not mention so far, but in fact, the kernel due to angular momentum is not one-dimensional. It's actually three-dimensional. This was mentioned also in the talk of Peter. And why is it three-dimensional? Because you don't have to track just the angular momentum, but you have to track the axis of the Kerr solution you converge to. Okay, recall that the Kerr solutions are axis symmetric. So you're going to converge, you have to track, even though your solution is non-axially symmetric, your perturbation is of course general, but you have to track what will converge to the axis in the limit. Okay, so in other words, so for these spheres, we're able to find such an intrinsic definition of angular momentum and to track the axis, the final axis of symmetry, if you want. Okay, so finally, let me, just maybe one further explanation on these spheres. Where do we actually have to construct these spheres? So let me go back to the picture of the bootstrap spacetime. These spheres are there to construct this sigma star. Recall that this sigma star is what rigidifies the spacetime, and recall that you want to properly choose it so that you actually see convergence to Kerr. So this is exactly to construct this hypersurface that you use these spheres. In fact, this surface, hypersurface, so three-dimensional hypersurface, consists of a concatenation of these very special spheres. Right? You take a one-parameter union out of these two-parameter spheres, you take a one-parameter union, and that constructs this very special hypersurface or last slice. Okay, so finally, let me mention what are the new aspects in the case of non-zero angular momentum. So on the technical level, there are lots of unfortunate things you have to do, but let me keep the discussions just at the conceptual level. So let me tell you what are the new conceptual difficulties, and I should mention at least if you work in the framework I'm going to present, in other words, in our framework. So what is the framework we are working with? So far, in fact, I did not really tell you how I solve the Einstein equations, but here I need to tell you a little bit more still, well, in fact, a little bit, since I didn't say anything. But yeah, so how do we solve it? We are in the context that was introduced in the proof of stability of Minkowski by Christine and Kleinemann, we are working with null frames. So the null frame is a generalization of an orthogonal frame in a Lorentzian spacetime. You could think of several generalization, but this is the generalization we're interested in. So what is this null frame? So you have E1, E2, E3, E4, and E3, E4 is a so-called null pair. In other words, it's a pair of null vector fields. And you should think of, in Minkowski, the generators of ingoing and outgoing light cones. In fact, in Schwarzschild, you should also think about it. Okay, so these are, let's say that E3, E4 are generators of ingoing and outgoing light cones. In other words, in Minkowski, if I write it in spherical coordinates, this is dt plus d. E4 would be dt plus dr, it's the outgoing one, and E3 would be dt minus dr. And then E1, E2 are orthonormal and orthogonal to E3, E4. So E1, E2, in the case of Minkowski and Schwarzschild, are simply generate the tangent space to the round spheres. Okay, of course, in perturbations, you can also define such null frames. There will be, for instance, E1, E2 will be tangent to spheres of intersection. They are not round spheres, but they are topological to spheres, and E3, E4 can still be generators of null cones. Now, as I said about the spheres, you don't want, usually when you define an object in perturbation, you always have in mind to what object should be converged in Kerr. So here, this null frame should not converge to any null frame, because of course there are infinitely many. It should converge to the special null frames that you prefer in Kerr and Schwarzschild, and that's the principal null frame. So why do you like this frame? Simply because it turns out that it diagonalizes curvature in Kerr and Schwarzschild, so it's a very important frame. And the important observation here is that the principal null frame in Schwarzschild is integrable, while the one of Kerr is non-integrable if the angular momentum is non-zero. And this is the main thing at the conceptual level, at least if you work in this framework, this is the main price you have to pay when you move from Schwarzschild to Kerr. Okay, so what do I call non-integrability? So integrability is the fact that E1, E2 actually span the tangent space of a two-dimensional manifold. Or you could also say, alternatively, that E3, E4 are the generators of the late cones emanating from the spheres. So that's integrable. And this frame would be integrable both in Minkowski and Schwarzschild, but unfortunately in Kerr it's not integrable. In other words, the principal null frame is such that E1, E2 do not span the tangent space of any manifold. In other words, they do not satisfy the standard Frobenius test, in fact, if you want. Okay, so why is this lack of integrability important? Why do I mention it? Well, for the following reason. It turns out that if you work in the context of null frames, all proofs, starting with the stability of Minkowski, so far in the field are always using integrable null frames. Or if you want S foliations, in other words, the fact that your frame is adapted to spheres. So here, if you want to work in perturbations of Kerr for non-zero angular momentum, this requires the first thing you need to do is to define new gauges. In other words, you need to define non-integrable gauges. So that's the first thing you should do. You should think of how defining new gauges. And then, so that's the first aspect. And then the next aspect is what does it create as problems when you estimate the equations? So the main problem comes from the fact precisely that E1, E2 are not tangent to the spheres of intersection, or the spheres foliating your codes. And the reason this is problematic is because when you try to control a Hodge-type system of elliptic type on the spheres, then if the derivatives are not tangent to the sphere, this is never going to work. So here, the way we went around this problem is actually to construct yet another structure, this time integrable. In other words, you construct another null frame, which itself is adapted to the spheres. And of course, as itself is useless unless you find a mechanism to go back and forth between the non-integral structure and the integral structure. Okay, and finally, let me mention another difficulty connected to these non-integrable foliations. And let me remind you that there are two types of estimates you're proving. You always, in these proofs, I think I mentioned it already earlier, there are always two types of estimates. Decay estimates for few derivatives and boundlessness of or energy type estimates for high and top derivatives. if you work with an integrable frame, usually you work, it's not usually, you always can work with the same integrable frame for both problems. It works, it's good for decay, it's also good for bondedness. In this problem, it turns out actually that it is not. In other words, we have a good, unless we could not find one that was working for both. So we found a very nice non-integrable gauge, which is well suited to decay estimates, but it is ill-posed. And for bondedness estimate, we found another non-integrable gauge, which is very nice to not lose derivative, to get a well-posed gauge and therefore recover top-order estimates. But it is not well suited for decay estimates. So then you have to live with the fact that you have these two non-integrable gauges. And in fact, in the end, you work with three frames, with three structures, two non-integral structures and one integral structure, or two integral frames and two non-integral frames and one integral frame. And that's how you can move from zero angular momentum to non-zero angular momentum. At least that's it for if you want the main conceptual difficulties. Okay, that's all I wanted to say, so I'll stop here. Thank you very much.
Thank you very much for your talk. Are there any questions from the audience? Please.
What about the interior of a black hole? I can imagine that technically it's quite difficult, but physically I cannot imagine the black hole without its interior.
No, sure. So the interior is quite different. You expect in fact instability, because Kerr has in the interior a very weird surface, which is called the Cauchy horizon. So it's a null bifurcated surface, beyond which there are infinitely possible extensions, which means you lose causality, which from the point of view of physics is not very nice. So the conjecture usually is that in fact it's unstable, and as soon as you perturb it, at least generically, you should see a singularity along this bifurcated sphere. So this is a different question. This is the question of proving in fact that if you perturb it, it's in fact unstable and you get a singularity. And this is why in the talk, I think, of Juan Maldacena, he was actually showing a Schwarzschild singularity, which is more, so I wouldn't say if it's space-like or null, you could debate, but at least you expect that there will be a singularity inside the black hole. So it will be, it's a very interesting problem and difficult, connected to what is called strong cosmic censorship. In other words, this business of loss of causality, but it's a different type of argument. You want actually to prove that the singularity forms along these hypersurfaces.
Questions, please. Can you perhaps remove it?
Right. Yes. You mentioned that the construction of these generally covariant modulated spheres is somehow related in some way. It's a distant descendant of the Huysken-Yau work, right? Some kind of distant. Actually, this work was refined, as we know, from the talk of Michael Eichmeier yesterday. So he mentioned these foliations by isoperimetric regions. So this is sort of the refinement of the old work of Huysken and Yau. But now, in your construction, which is a codimension 2, of course, is it possible to say that somehow it's related to specifying mean curvature and torsion, perhaps, or something like that?
Yeah, so exactly. This is the geometric quantities I did not show, but they involve it. Let me give a simple answer, which is yes, it is related to prescribing both mean curvatures, the outgoing and ingoing one, and prescribing the analog of the torsion, which is mass aspect function. So it is exactly analogous to that. Now, at a technical level, due to the fact that when you're close to K or Schwarzschild, far away, you're also close, in some sense, to Minkowski, there are some degeneracy at, let's say, spherical harmonics L equal to 1, which is due to the presence, due to the fact that at the Euclidean level, you could move your spheres around in translation and Lorentz boots. So Lorentz boots and translation force you to modify the construction at L equal 1 nodes specifically, but for the rest, it's exactly this, yeah.
Right.
More questions? We have some online questions? No. Okay, well then let's thank the speaker again
Thank
for
you.
a nice